Hello and welcome to our video for the 2022 Physics Paper 2. So we've already done Paper 1 on our YouTube channel and we've also done a fair few of the other papers. So keep an eye out for that as well as for the other sciences. So we're just going to jump straight into this paper. Okay, so question 1. Two spaceports are stationary relative to each other. Astronaut A moves from one spaceport to the other at a relativistic speed and observes the light on both spaceports turn off at the same time. So I'm already thinking, okay, this is talking about a simultaneous event happening for astronaut A. Astronaut B is at a stationary position, equally distanced relative to each spaceport, and observes the lights turn off one after the other. Explain why astronauts view these events differently. So I'm not going to really write down my answer here. This isn't really a working problem, but what I'm going to do is kind of just discuss the reasoning behind the answer. So what we have is, I guess, in the whole context of special relativity, we have simultaneity. So this refers to two events occurring at the same time or occurring simultaneously from the perspective of an observer. Now, what we know in simultaneity is that two events can only happen spontaneously. So like for astronaut A, the lights going off at the same time can only happen in one inertial frame of reference. So when I say an inertial frame of reference, one of the frames that is either moving or stationary. So this is relativity of simultaneity. So when we think of our special relativity, some of the two postulates, that is also that's one of the postulates, I guess, a little bit further broken down. So therefore, due to astronaut A observing that simultaneity, that's in its inertial frame of reference, astronaut B loses simultaneity. So that's going to be your answer to question 1. So definitely hop online, have a look at the QCAA's annotated example, and also have a look at our example. We've posted a written up version online. Check the link in the description. All right, so question 2, contrast the properties of up quarks and tau particles. So again, this is going to be more of a written response. This time I'll just put some dot points down because it's a little bit of an easier question to write some dot points. But an important thing that you should be fairly familiar with by the time it comes to your external exams is some of these cognitive verbs. So contrast. Contrast means you need to display recognition of differences. So you should be able to juxtapose some of the differences between different things. And in our case, we're looking for the differences between up quarks and particles. So I guess to start off, both are fundamental particles. Now let's break down specifically stuff about our up quarks. So up quarks versus our tau particles. So about our up quarks, they experience strong nuclear force. So again, this is going to be some memory stuff that you need to know when it comes to specific stuff about your standard model and particles. So strong nuclear force. Strong nuclear force, as well as quarks can be added or can be combined. So I'll just write can be combined to form other particles such as mesons and baryons. Whereas on the other hand, our tau particles, they're part of the lepton group. So they're part of the lepton group. They experience weak nuclear forces. So I'm just going to write weak here as well. These can't be combined. I guess we'll use that word in contrast. In contrast, they cannot be combined to form other particles like quarks, so cannot be combined. And that's going to be our answer again for question 2. Again, I'm going to say, check the link in the description as well as hop onto the QCAA website and see what their exemplar answer is. All right, so question 3, negatively charged oil drops were placed in a uniform electric field generated by two parallel plates. By altering the applied voltage between the plates, the oil drops were suspended in the air between the plates. The graph shows the electric field strength required to suspend negatively charged oil drops of varying weight. So having a quick look at, the diagram displays that we have an electric field here, And we also have our oil drop suspended, and what we can tell or from the written breakdown of the scenario as well as the graph is that they're changing the oil drop mass, and as a result, to keep that oil drop suspended, they have to increase the electric field strength. So this is that relationship we got here on our y-axis versus our x. So a very important thing when we start seeing questions with graphs is start thinking about, okay, what is my x-axis? What is my units? Is it itself got a relative formula? Here our x-axis is measured in newtons or force. So I'm going to say x is equal to force already as a note. And my y-axis is electric field strength. So our electric field strength is denoted as E. So I know y is equal to E. So let's continue on and see what the questions are. So determine the average charge on the oil drops. Show your working. So the average charge on our oil drops, let's think about the scenario here. It's going to be related to some of the information in this graph. So I know the graph follows a linear trend. Y is equal to mx. Now I'm not going to put a plus c on this because I know this graph should intercept at 0, 0. Some rationale behind it is I could draw a trend line and could see, okay, it does cross through 0, 0 or really close. The other thing that I can rationalize is if there's no oil drop, there's no force for it, so there's going to be no electric field strength that needs to suspend no drop. All right, let's continue through. I know as well, the formula is, or let's go back before I throw in a formula, y is equal to E, that's the units, it's our electric field charge. X on the other hand is equal to, or measured in newtons, which is our force. I'm going to jump into my formula book, look for an equation that looks similar in my magnetic and electric fields kind of topic. I end up getting, so first I'll substitute these values in, E is equal to m multiplied by F. I have a formula which is E is equal to F over Q. So that is our electric field strength question, or electric field strength equation. I can write it another way just to show that 1 over Q multiplied by F is going to be equal to our E here. So I can now state or get to a point where I'm trying to calculate that Q, the charge of my oil drops. So I know in my equation for y equals mx, now down to E is equal to mf, m corresponds to our 1 over the charge value. So I need to figure out what the gradient is to then help me solve for what the charge is. So let's go up. I'm not going to write in this space, but when you're doing your exam, communicate in the appropriate marked out areas for you. So let's find what m is equal to. So I'll go back to red. So m is equal to the change in y over the change in x. So the values I'm going to pick is, I'm going to choose up here. So that is 3 times 10 to the 19. Why is it 10 to the 19? Because here on my axis it says so. So I'm going to clear out that. So 3 times 10 to the 19. My next point I'm going to pick is down here, minus 0.5 times 10 to the 19. Now, other students or other ways you can solve this would be drawing that trend line in and then picking a point along the trend line. I like to use these two different points on the graph at each end, or picking points that are quite relatively easy to get an actual value for because it crosses one of the axes, or crosses, like this instance, our 3.0 at the top here. Okay, so the value that corresponds to 3 times 10 to the 19 is 50. So it's going to be 50 on the bottom minus 10. So 10 is where I get that 0.5 charge. That ends up getting me, once I punch that into my calculator, 6.25 times 10 to the 17. So I'm going to go back down now. So I know m is equal to 6.25 times 10 to the 17. Therefore, 6.25 times 10 to the 17 is equal to 1 over q. And so I can just rearrange that by doing the inverse of that side. So 1 over 6.25 times 10 to the 17, again, I keep on repeating myself, is equal to q. Therefore, q is equal to 1.6 times 10 to the negative 18, and our charge is coulombs. I'm going to quickly check to make sure that my charge is coulombs going through. So in this equation here, or in our calculation for the gradient, we had oil drop in newtons, so I'm happy with that, and also our electric field charges in the appropriate units here. And so therefore my charge is in coulombs, not millicoulombs or anything of the sort. I'm making sure I used all the SI units for my calculations as I went through the question. So that means to 2 sig figs, 1.6 times 10 to the negative 18, and it's already got my coulombs there. All right, another oil drop was suspended between the plates with an electric field strength of 2 times 10 to the 19 volts per meter. Determine the work done to move this oil drop a distance of 5 millimeters towards the negatively charged plate. Show your working again. All right, so we're going to use our graph again to figure out, first and foremost, I need to know, or I have an equation to figure out the work done. So let's figure out the equation first. Work is equal to force times S. S is our displacement here. So it's one of the equations you're given in your formula book. So I need to first figure out, with an electric field strength of 2 times 10 to the 19 volts per meter, what does that correspond to on the graph as a force? So there's two ways I can figure out the force. So using my equation or using the graph, we'll scroll back up and have a look. So at E equal to 2.0 times 10 to the 19 volts per meter is has a F equal to, so let's scroll up, so we're looking for 2.0. So I'm looking at this line here, 2.0. I'm thinking my trend line sits somewhere along here. I'll try and tidy that up. My trend line sits somewhere along there, and I'd be happy to say maybe about a 33-ish kind of value. So that could be 33, and that's newtons. The other way to do it would just be using the formula we already calculated. So using our E is equal to F over Q. We know what Q is. We did it in the previous question. So we can then rearrange that to F is equal to E times Q, which is equal to our 2.0 times 10 to the 19 multiplied by our charge, 1.6 times 10 to the negative 18. And when I punch that in my calculator, I get 32 newtons, so 32 newtons. Now for this, I'm going to continue and use the 32 newtons because it's using the formula we previously had. And that trend line could be slightly off. I'm making an estimate there. All right, so 32 newtons, the displacement is 5 millimeters. Remember, we're working with things in SI units. So our equation for work is equal to F times S. Work is equal to 32 newtons multiplied by millimeters to meters is going to be times 10 to the negative 3, so 0.005, and that's going to get me 0.16. And the important thing is, what are our units for work? It's measured in joules. So that can be converted to 1.6 times 10 to the negative 2 if we want to make it a little bit more neater, and joules is our answer there. All right, so question 4, a stationary object on a frictionless inclined plane is connected to a 15 kilogram weight as shown. Calculate the mass of the object on the inclined plane. So let's first, I guess, do some steps through, go back what we know. So we have a 15 kilogram mass here that has a force pulling down on it, and that's going to apply tension to this pulley as well and pull down. So that same force here, I'm going to say F of T, force of tension, is going to translate to that piece of wire up here. So that is going to be our force of tension. We also have, let's draw our other forces on. We have the force of gravity, which is perpendicular, not to the slope, but to the ground. So F of G, this is of the box. Then we have our normal force. So our normal force is always drawn to be perpendicular to, so when I say perpendicular, at a right angle to the surface the object is resting on. This object is resting on a slope here, so it's perpendicular to that slope. So that would be our F normal. And we also have, finally, our other force, which would be the force that's actually pulling the object down the slope, which is one of the translations of our force of gravity on the box, which we can say force of F. Now, there are two ways to solve this solution. The first solution is to think about is going to be a very straightforward one using, I guess, a lot of your memory. The other solution that I'm going to talk through as well, which some students feel free to skip through, is just going to be a little bit more of a breakdown and a representation of some of our force vectors and how they interact with one another. So we know, because reading this stem, this object is stationary, or this box is stationary, that's telling me, so I'll write solution 1 here. That's telling me that this force here is going to be equal to the force of tension from our 15 kilogram mass, because it's pulling it, should be pulling it up the hill, but it's not. The object is stationary. So these two forces are equal to one another. So I will communicate that with F. F is equal to my force of tension. So I know FF is going to be equal to, so this is just straight from memory what you should be learned or should know off the top of the head. If not, we'll talk through the other way to calculate FF. So FF is going to be equal to FG multiplied by sine theta. Theta being the angle of the inclined plane, 35 degrees. FT, on the other hand, because we know it's attached to a pulley and a 15 kilogram mass, that's going to be 15 multiplied by g, which is gravity, mass times acceleration. I'm going to leave gravity as g for now because you'll see we'll end up cancelling that out. Now, Fg is equal to the mass of the block, so this block here, sitting on our slope, multiplied by gravity. So that's going to be mass multiplied by gravity, still multiplied by that sine theta, because we only substituted this portion in for our Fg. Sine theta is equal to 15 times g. So let's simplify this through. Our g's can cancel out, so if I divide it from one side, it will be divided by the other. So I'm left with m multiplied by sine theta is equal to 15. Therefore, m is equal to 15 divided by sine theta, and I'm going to substitute that 35 degrees in, and that's going to get me 26.15. Now kgs, just checking through, the units I'm using is degrees, in my calculator is degrees, not radians, as well as 15 kilograms is where I got that from, and that's in kilograms. So that is going to be my answer. So my answer here is, to two significant figures, is actually 26 kilograms. Now solution 2 is going to get us to think about, so again, it's a near identical method, but it's going to help us visualize the relationship between our FF force and our force of gravity. So our FF force, if I was to draw it as a vector, points down the slope. It's parallel to our slope. That is our FF. But we have our force of gravity, which is pointing perpendicular to the ground. So FG. Now that angle, I'll use it in green, that angle at the top here is going to be 55. And the reason it's 55 is because if I draw or think about my triangle, it's 35 down here. And so if I make a right angle triangle, that must be, that angle up there is corresponding to that angle there. So that's 55 degrees. So 55 degrees in that angle. And then we have our normal force, which is what points upwards here. So we're breaking our force down, where our normal force is just the opposite direction of our force of gravity, or sorry, is just the opposite direction of the x component that would be resting on the slope. So Fn in this case. But if I was to flip it around, it would just be the F x component, G x component, and thus FF could be corresponded to FG in the y. Oh, sorry, I've got them around the wrong way. That would be GY, and that would be GX would be our FF. But I'm going to keep it as FF in this case. So we know what our FG is equal to, or I'll go through the steps. FF is going to be same as before, is equal to F of our tension. FG is FF is equal to FT, which is 15 multiplied by 9.8. And we know that FG, this FG here, is equal to mass times 9.8. I don't know what that M is, but I do know that another way to calculate Fg would be saying that it is, because it is the hypotenuse of our triangle, because that's a right angle there, it would be FF divided by cos 55. So I'm using my SOHCAHTOA, using our cosine and adjacent and hypotenuse, and I've rearranged it. So my next statement to that would be substituting my FF here, that 15, times that 9.8 on top of the fraction. So 15 times 9.8 over cosine 55, which is equal to, again, that other FG value, m times 9.8. And I can then rearrange that to getting m is equal to 15 over cosine 55, which again gets me 26.15 kg. Now, I wouldn't recommend doing solution 2. Solution 2 is a way to kind of rationalize and figure out, okay, what your FF is equal to, or figuring out, okay, what's the relationship between your FF and your FG. It's a way to, I guess, help you think about a problem if you forget the simple solution or the simple route as solution 1. All right, so question 5, the Feynman diagram for a particle interaction is shown. Describe the particle interaction taking place. So the QCAA has a really good resource under the teaching material, which is just their breakdown of the Feynman diagrams that you need to know. So make sure you're very familiar with that document, because it has 3 diagrams, I believe, or 4, including the different breakdown for your neutron decay, knowing what the quarks are that correspond to a neutron and a proton. So describing this particular diagram is, we know it's a reaction between an electron, E negative, and an E positive and a proton. So it's a reaction. I'm going to do it very shorthand. Hop online, have a look at their explanation or their written response to this. But it's a interaction or reaction between an electron, so that's the E negative, and a positron, which is our E positive. Now, this particular diagram, so you should know the name for it, is Barter scattering. So I will write that here. And the other thing that we need to know is what is happening in between our electron and our positron here, which is going to be the exchange of a photon between the two. So photon exchange between our E negative, which is our electron, and our E positive, which is our positron. And then finally, what else is happening here is, after the exchange, these both go off in different directions, or they change their velocity, because remember, velocity is also a vector quantity, so the direction is also a component of a velocity. So change, or all right, after exchange, both change velocity. And remember, velocity also constitutes the direction as they move away. So that's question 5. All right, so question 6. A light was shone onto a metallic surface and subsequently released photoelectron passed through a magnetic field. Part A, identify the direction the photoelectron would have curved as it passes through the magnetic field. So our photoelectron is coming into our magnetic field, so I'm just going to assume, like, we know it comes in at a slight angle here, but I'm just going to draw it coming in completely perpendicular to the surface. And so what I'm going to use is my right hand rule. Now, I'm not going to state like what fingers I use for mine, because I don't want to, I guess, confuse some students, but what you should end up working out is that your magnetic field is into the page. So if it's not stated and you're given the x's, the way that I remember an x corresponds to into the page is like there's treasure under there. And that's the way it's pointing. An X points down into the ground because there's treasure under there. And so that's the way a magnetic field is going. And if it's a dot like that, that's the point of an arrow looking at me. So it must be looking at me or coming out of the page. So that's the way I remember the difference between an X and a dot for into and out of the page. But what you should get is when you do your right hand rule, you get your, so here I'm going to draw an arrow, you get your velocity or movement of your electron upwards. You get your, now there's a very poor three-dimensional, you get your magnetic field into the page, but you get your force pointing towards the left. Now, the way that I remember this is for a positively charged particle. So if it's a negatively charged particle, I don't need to change my hand rule or anything like that. The only thing I need to remember is that if it's a negatively charged particle, it's going to be forced in the opposite direction to if it was a positive. So that's my positive, and that would be my negative. So my answer would be curves to the right. And that's going to be using the right-hand rule. All right, so continuing for question 6. The graph shows the maximum kinetic energy of the photoelectron as the frequency of light that was charged. Or that was changed, sorry. So what we have here is, again, I'm going to quickly look at the graph and see what I'm given. So I'm given the maximum kinetic energy in electron volts. That's an important note. So it's essentially the EK that's being ejected, but in EVs. And here on the x-axis is we have 1 over the wavelength. So our x-axis is equal to 1 over the wavelength. An important thing is that wavelength is times 10 to the 6. All right, so let's continue on. So part B, determine the work function for the metal, show your working. So what's our work function? So we know the scenario relates to our photoelectric effect. So EK is equal to HF minus W. W is our work function, H is Planck's constant, F is the frequency at the light that we hit on the incident light that's hit onto the metal. So we know that for, I guess, an electron to be ejected, you have to overcome that work function. So if I go back and have a look at my graph, the point where this, if I was to put a trend line through, the point at which this function intercepts the x-axis and then actually produces energy would be the work function. Or another way to state that would be at an EK equal to 0, we would, oh, that's not negative 0, equal to 0, we'd then be able to solve for what our work function is, because that is the energy we have to overcome to eject something. So if I then substitute my 0 in for my EK, I end up getting a statement, 0 is equal to HF minus W, therefore W is equal to HF. And what I need to do now is have a look at my statement. I end up getting not a frequency, remember, for my x-axis. I end up getting a wavelength. So we've done it in previous questions. We know that frequency is equal to C over wavelength. And I then know, okay, my work function is equal to HCF. Where do we cross the x-axis, or at what point do we get an EK equal to 0? That is when that's our x-intercept. X is equal to approximately 1.65 times 10 to the 6 meters to the negative 1. So I'm just looking here, that is this value here, that 1.65 on my x-axis. And remember, we've already made the statement that, so I'll continue it over. We made the statement before that x is also equal to 1 over the wavelength. So we first need to rearrange this. So we get wavelength is equal to 1 over our x, which is equal to 1 over that 1.65 times 10 to the 6. That ends up getting us a wavelength of 606 times 10 to the negative 9 meters, because we're working with normal units. Another way to look at that is 606 nanometers is the wavelength. So going back to our statement that we've worked out here, W is equal to Planck's constant, C over wavelength. we end up getting W is equal to hc over wavelength, which is equal to our Planck's constant, 6.626 times 10 to the negative 34. Then multiplied, what's our speed of light? 3 times 10 to the 8 over our value of 606 times 10 to the negative 9 is our wavelength of light, and that's in meters. We end up getting an energy of 3.27987 times 10 to the negative 19, and our answer is going to be in joules here because we're only using our work function here, and we've used the appropriate SI units as we continue through. What does it want? It wants 2 sig figs. That is just going to be 3.3 times 10 to the negative 19, and that is joules. All right, so we're now up to part C. If the strength of the magnetic field is 5 UT, determine the maximum radius of the photoelectron's path through the magnetic field when light of wavelength 450 nanometers was shone onto the metallic surface. Show your working. So this is quite a complex question, and I guess it's also, noted by it being worth 9 marks over here. So let's break down the scenario, what's happening first. So we have our magnetic field going into the page so a page over, we saw the diagram, magnetic field going into the page, and we will eject an electron. And remember, our electron is negative charged into a magnetic field, and we know if an electron is shot into a magnetic field, what it will do is experience a force as long as that electron is traveling perpendicular to the magnetic field. So that force, using our right-hand rule, we determined heads towards the right. And so what ends up happening is, I will use green here, it will rotate around a radius here. So that would be R, and that's R. So we need to know a couple things of what happens. So let's restate quickly what's happening. Our electron moves into a magnetic field, and as an electron moves into a magnetic field, it will experience a force. And we know that force directs it towards the right, so that's how it will rotate. So one thing we can start thinking about is maybe we can know what that force is. So the force that's going to move our electron is going to be F is equal to QVB sine theta. And in this case, our sine theta is equal to 90. Why is it equal to 90? Because our electron is perpendicular to the mag field. So theta equal to 90 because it's perpendicular. So I'm just going to draw that right angle there, perpendicular. So therefore, we know that. What other, values do we know before I even substitute any in? We know Q, what's our charge of an electron? It's in our formula book, 1.6 times 10 to the negative 19. Some other information they've given us is what's the strength of the mag field? B is equal to 5 UT, which is equal to 5 times 10 to the negative 6 Teslas. So again, that's in our formula book. The only thing we don't know is the velocity. So we don't know the velocity that this electron goes in to our mag field. So what I'm going to do is, we're going to have to figure out what our velocity is. So I'm going to just go over the page. So I know velocity can be found using equations such as kinetic energy, EK, is equal to half mv squared. The other thing is I don't know the kinetic energy, but I do know based on the scenario that our kinetic energy, it's a photoelectric effect question, is ejected, which is equal to hf minus w. And I also know that we weren't given the frequency of our ejection, but we do know the wavelength, which was 450 nanometers. So h is c over wavelength minus our work function, or w. So we can figure out the kinetic energy as being equal to 6.626 times 10 to the negative 34 over 3 times 10 to the 8 speed of light over our 450 nanometers, but nanometers to meters is times 10 to the negative 9, minus our work function, which we stated in the previous, which was 3.3 times 10 to the negative 9. And then as I continue through now, I end up getting an ejection energy of 1.12 times 10 to the negative 19. And here we're working with joules. And now I can rearrange our EK, or kinetic energy formula, with our velocity in it to figure out what the velocity of the ejected photon is. Or sorry, ejected electron. So that ends up being EK, I'll restate it, is equal to 1/2 mv squared. 2 EK is equal to mv squared. V squared is equal to 2 EK divided by m, and to move the square, we just square root both sides, and that's that square root there. And I'm going to substitute in my values. So it's the square root of 2 multiplied by our 1.12 times 10 to the negative 19 joules, the energy of the ejected electron, divided by the mass. Our mass is in the formula book for an electron, and that's going to be 9.1094 times 10 to the negative 34. And we end up getting a velocity, remembering our SI units as we go through, is going to be 49518.76 meters per second. Otherwise, I'm just going to go to 2 sig figs like the rest of our questions, 5.0 times 10 to the 5 meters per second. So now I have my velocity for that original equation, and we can put that as our 5.0 times 10 to the 5 here, meters per second. So the reason we're using this force equation is because we know from our circular motion, the F net of circular motion is going to be equal to the force that moves the electron. So I can say that force is equal to F net, which those two equations would be, so F net of circular motion is equal to our QVB. So that QVB has come from this equation here. The reason I've dropped the sine theta is that sine 90 is equal to 1. Is equal to our F net. Our F net equation is equal to mv squared over our radius. So that's the thing we're trying to calculate, is our radius here. So what we're going to do is rearrange the equation. Therefore, r is equal to mv squared divided by qvb. We can simplify that because that v squared can be divided by v. So we end up getting mv over qb. We can substitute in. What's our mass? Again, it's 9.1094 times 10 to the negative 31. I think I might have said 34 up here. Should be 31. Multiplied by our velocity, 5.0 times 10 to the 5. All divided by our charge of an electron, which is 1.6 times 10 to the negative 19. Multiplied by the magnetic field strength, which was 5 times 10 to the negative 6. We end up getting a radius equal to 0.5639 meters. So remembering our SI units as we go through, radius to 2 sig figs, 0.56 meters. Fantastic. So it's quite a fair bit of working to go through for that part C, and hence why it's worth its 9 marks. A tip for it would be looking through some of your formula book. Okay, what formulas have some related components between them that can help me solve this problem? A tip for these types of questions is I'm always going to say revision, revision, revision. If you're not exposed to a question similar to this, you'll never be able to solve it on exam day, or when you do go to solve it, it's going to take a lot longer than it should if you did see a similar question. All right, let's continue on. All right, so question 7. 2 asteroids experience a gravitational force of 3.3 times 10 to the 3 newtons between them. Their masses are 2.7 times 10 to the 17 kilograms and 6.1 times 10 to the 15 kilograms. Calculate the distance between the 2 asteroids, show your working. So a fairly straightforward question that you would have done fairly early in the year or in your circular motion and gravitational content. So we're going to look for our formula book. If you have no idea what formula you're looking for, in this case, we're trying to find the distance between them. I'm going to give you some hints. Always look at what some of the variables are. Some variables may be red herrings, but list them out. We're given the force, so we're given F, we're given mass of two different objects. So M can be capital M here and lowercase m can be the mass for the other. So I'm going to get, or find my formula. Force is equal to G for gravitational constant, m over our radius squared, which is the value we're trying to calculate. So I'm going to rearrange this formula. I know I'm trying to calculate radius, therefore radius squared is going to be equal to G m over F, and then therefore radius is going to be equal to the square root of our G m lowercase m over F. And we can just straight away substitute all those values in. So it's a horrible square root bracket. So square root G, gravitational constant, 6.67 times 10 to the negative 11, multiplied by the mass of one of our asteroids, which is going to be 6.1 times 10 to the 15, multiplied by the mass of another one of our asteroids, 2.7 times 10 to the 17, all divided by our force between the two objects, which is 3.3 times 10 to the 3 newtons. Before I punch it into my calculator, I'm going to scan. We're given kilograms, our SI units, newtons and kilograms here. So I know the radius I get should be in meters. So I punch that into my calculator, I end up getting 57696935548 meters. And I'm going to convert that to 2 sig figs, like the question's asking me now. So that is going to be a radius equal to 5.8 times 10 to the 9 meters. And so that's our question 7. So 5.8 times 10 to the 9. All right, so question 8. The graph shows the gravitational force experienced by a rocket of mass 750 kilograms as it approaches an asteroid. So again, we've got a graph question here. I'm going to break down. My x-axis is x is equal to 1 over r squared. And also my y is measured in newtons, which is also known as force. And what we've got here is probably a fairly important thing to denote off the bat is it looks very similar to a linear model. So I'm going to state that as I go through. So this is a linear model graph. So determine the mass of the asteroid, show your working. So we've got the force as you get further away or closer to the radius, because remember our x-axis is 1 over the radius squared. So as you're really far away from the radius, you have a lower gravitational force here. And the reason our x-axis is actually quite a small value when you're far away is because it's 1 over the radius squared. So as the radius gets larger, it then gets squared, and then 1 is divided by that value, and it ends up being a smaller value. And then as you get closer to the object, your 1 over the r squared gets smaller, but your force gets larger due to you getting closer to the object. And that's just following. Now, it's very similar to Newton's law of universal gravitation. So let's continue going through because we're trying to determine the mass of the asteroid. So if it's a linear model, it's y is equal to mx. Now, again, I'm neglecting the plus c because if you're so far away, infinitely far away, you should have no gravitational force experienced by the rocket. Now, this, I'm going to then substitute our y value in. We found out y is equal to f. M is our gradient multiplied by x, which is 1 over r squared. Now, that is very, very similar to, again, what I said before, Newton's law of universal gravitation, which is a formula F is equal to G, capital M, lowercase m for the two bodies. So one can be the asteroid, 1m can be the mass of the rocket ship, divided by r squared. And again, that is very similar, or to make it look even more similar to our linear relationship model above, what I can do is just do G, m, lowercase m, multiplied by 1 over r squared. And therefore, I get this new statement, or this realization that gradient, the gradient of my slope above, is going to be equal to G, m, m, because this here maps up to that m there. And I don't want to write m is equal to g, m, m because we've got too many m's. That's why I've written it as gradient is equal to our g, m, m. So we know what g is. That's our gravitational constant. We know what one of the m's is because that's the mass of our rocket ship, which is 750. So to figure out the other m, we need to figure out what the gradient is, and then we can just rearrange and solve. So our gradient is always going to be equal to change in y over the change in x. I'm going to pick some values on the graph. So I'm going to pick 45 and the 26, so the 45, 26, and I'm going to also pick this value here at the 10 as well with a gravitational constant of 6. So I'm using the appropriate units here. So it's the y is in 4, so it's 26 minus, it was 6 newtons. So I'm just going to check. So yep, that lines up to 6 newtons on my y, and this is about 26 here. All right, now my x is going to be the interesting one. Our x is at times 10 to the negative 13. So that's going to be a very important thing to remember. So it happens at, we said this value is at 46. So that's going to be 46 times 10 to the negative 13 minus our other x value, which is that 11-ish here. At 11, I'm going to say maybe 11.5. 11.5 times 10 to the negative 13. That ends up getting me a gradient of 5.797 times 10 to the 12. And then we can just continue from there and rearrange. So I'm going to just pick a different color to continue through. So we've said our gradient is equal to gm lowercase m. Therefore, 5.797 times 10 to the 12 is going to be equal to g, which is 6.67 times 10 to the negative 11, m, which is going to be the mass of our asteroid, and lowercase m, which is 750 kilograms. I rearrange it to this gradient, 5.797 times 10 to the 12 divided by our 6.67 times 10 to the negative 11 multiplied by our 750, and that's going to equal 1.1588 times 10 to the 20 kg. And to confirm that it's kg, I'm just going to quickly check through my gravitational constant. I'm using the appropriate units because I've taken that from the formula book. And the other thing is our forces in newtons, and I made sure to convert this value, that 46, and as well as that 11.5, times it by 10 to the 13 to get it into our meters. All right, and that's going to finish that question. So answer would be to 2 sig figs, 1.2 times 10 to the 20 kg. All right, so question 9, the final question of paper 2. So a person spins an object 4.3 meters above the ground in horizontal circular path of radius 0.8 meters. They release the object horizontally, allowing it to travel to the ground. Now part A, calculate the centripetal acceleration of the object before it is released, given it takes 5 seconds for the object to complete 12 revolutions. Show your working. So we're trying to calculate the centripetal, so I'll get my pen, centripetal acceleration. And that in our formula book is noted as AC. And so to calculate that, we're going to use our formula AC is equal to v squared over the radius. So we don't know the velocity, we do know the radius. It's highlighted to us as 0.8 meters, and that's in the appropriate SI units, but we don't know the velocity that it is spinning around. So to calculate our velocity, we're again going to use a formula in our circular motion, or group 2 of our circular motion formulas, where v is equal to 2 pi r over t. And so t is our period here. So t is the time it takes to complete one rotation. So we're going to do the 5 seconds divided by 12, which ends up getting us, or I'm not even actually going to calculate a value because I don't want to have a reoccurring value. I'm just going to punch that straight into my velocity formula. We've already said radius is equal to 0.8, so our velocity is 2 pi 0.8 divided by our 5 divided by 12. And that's going to get me a velocity of 12.0637 meters per second. And I'm happy that it's meters per second because my period's in the appropriate units, and same with my radius. All right, so to continue on now is our AC is equal to v squared over r which our v squared is going to be now 12.0637 squared divided by our 0.8, which then gives us our units, which is going to be AC is equal to, or gives us our acceleration, 181.916, well, it's a tiny 6 meters per second squared. And so another way to rationalize your answer, if you square the velocity, it's meters squared per second squared. Meters squared per second squared divided by meters is just going to get you your meters per second squared. 2 sig figs, that rounds to 180, and our units meters per second squared for acceleration. So part B, calculate the total horizontal displacement of the object after it's released. Show you're working. All right, so in our scenario, we have a person standing, and what they have here is they're spinning that ball about 4.3 meters off the ground. So here's the ball, and it's going in a circular motion. And what we know from circular motion, the moment it's let go, it will go off at a tangent to the circle. So I'm just going to redraw the ball at a different location. So I'll give this guy a head. The ball's over here, and it's going in a circular motion like that. This isn't too critical to it, but the moment it's let go, it will traverse off at a tangent and then go towards the ground. So some things that are relative or important for our velocity is it only has a horizontal velocity, right? And the reason I know it has a horizontal velocity because the object in the stem, it says the object is horizontal, is going to be released horizontally. So object horizontally or released horizontally. So we figured out the velocity in part A. So that velocity is going to be the launch velocity, or the Vx, we can think of it, is going to be equal to 12.1 meter per second. And we also know the height that it's launched from is 4.3 meters. So what we're trying to calculate is the range of the object. So the distance from the moment it's released to the moment it hits the ground here. So range x, essentially. So we know the range is going to be equal to, so Rx is equal to the velocity of x multiplied by time. And that time is the time it takes for the object to hit the ground. So we know the object will hit the ground because there's going to be a horizontal and there's going to be a vertical component of this projectile motion. So we know the formula we can use is Sy is equal to Uy, the initial velocity at the y, multiplied by time plus 1/2 at squared. So in this case, what's our Sy? Well, the Sy, when it hits the ground, if I consider this position up here as 0, 0, that Sy would be negative 4.3 meters because it falls 4.3 meters to go to the ground. Uy, it has a 0 velocity in the y direction. It's only the horizontal, remember? It's only going horizontal. It doesn't have an angle of launch, so it has no y component. And the t in this case, we're trying to solve for it. So it's 0 multiplied by t plus 1/2 multiplied by the acceleration. And that's negative 9.8 because gravity is working in a downwards direction, or acceleration itself is a vector quantity, so we have to give it a vector. And since I've given negative 4.3 as the displacement, I'm also going to give a negative 9.8. And it's going to be multiplied by t squared. I'm going to go over the page now. I'm going to simplify it. I get negative 4.3 is equal to 0 times time is just 0. So it's going to be plus it's going to be negative because it's 1/2 multiplied by negative 9.8. So negative 4.9 t squared. I then end up getting t is going to be equal to the square root of our negative 4.3 divided by negative 4.9. And that's going to get me a time of 0.937 seconds. So that's the time it takes to hit the ground. So I can just go back to my range formula right here and substitute our values in. So range is equal to our Vx multiplied by time. Our Vx was 12.1 multiplied by our time it takes to hit the ground, 0.937, which ends up getting me an Rx value of 11.337 1.77 meters. 2 sig figs, just 11 meters. And I can't finish it off with it being green. We've done red for every single box solution, so it is 11 meters. And that's going to conclude paper 2 for the 2022 physics paper. All right, thanks for watching.